Hi kids! This lecture is going to introduce two concepts that you're going to be hearing a lot about over the rest of the year. The first is the idea of a system. So a system is basically finding ways to include multiple objects in the same physics analysis. Instead of having to figure out what's happening to every single object around you, you can lump things into bundles of objects called a system. And the second idea is known as conservation, which you've probably heard that vocabulary word before and know that it roughly means to keep the same amount of something. But what you may not know is that there are 4 conservation principles in physics that are kind of the number 1, 2, 3, and 4 laws of physics. They're the things that can absolutely not be violated by anything. And when physicists do a new experiment or a study, one of the very first questions that people ask is whether it violates the conservation principles. So these are the big ideas of the year, I would say, and so understanding conservation is important. We're going to introduce the first one today, which is conservation of mass. So a system is a way of separating an object or objects from everything else so we can analyze just what's occurring in that system. For example, I could make a system containing a purple block, and the way I am showing you that it's a system is I'm putting a box around that system. It's a pretty boring system. There's just one object in it, but sure, this is a system with a purple block. I could make a more interesting system. That is a Bugatti Veyron, which is Miss Nichols' favorite car. And that system looks like a single object, but of course the Veyron is made up of a whole bunch of little tiny parts. Usually those little tiny parts move together, so it makes sense to include all of them together in a single system. You may notice that one of those boxes around the system is solid line and another one is dashed line. That's 2 different types of systems, which we'll get into in a minute, but I wanted to point out that there is a difference there between the type of system that I'm making. So the solid box around a system is showing that this is going to be a closed system, and that means that I'm isolating the object in that system completely from everything else around it. We're pretending that nothing else exists except for just the stuff inside the system. So if I wanted to make a real truly closed isolated system containing a piece of candy, that's a Hi-Chew candy for those of you that don't recognize it, I'd have to think if that Hi-Chew candy was truly isolated from everything else. And the problem is that Hi-Chew is probably sitting on a desk. So really, if I wanted to isolate it, I have to include the desk in that system as well. Of course, you're probably realizing that that desk is touching things and other things are interacting with it. In fact, it's touching the earth. So now we have to include the earth in our system if we want to make this a real closed system. And the earth, though, isn't moving on its own. The Earth is part of our solar system, so now we have to have the whole solar system in our system. And it turns out that our solar system is being impacted by solar systems around us and other stars, so really we need to include the entire universe. There we go, that's a closed system. The point here is that it's nearly impossible to truly create a closed system because everything on Earth is interacting with lots of other things. The only truly closed system is the entire universe itself. However, we often pretend we're making a closed system. We kind of do a little thought experiment where we do our best in our brains to separate the object from everything else. So we will use closed systems in this class. You should know they're probably not really truly closed, but we're doing our best to isolate them from everything else around them. So the other kind of system, the one with the dashed line around it, is known as an open system. And in open systems, outside objects can exert forces on the objects in the system, which can change the object's position or their motion. And objects can also move in and out of a system. So if I made an open system containing a 100-gram candy bar, delicious. I love Halloween because I get lots of those. You probably realize that there are some objects exerting forces on that candy bar. For example, the Earth is probably pulling down on that candy bar, and the table is probably pushing up on that candy bar. Those forces might change the motion or the position of the candy bar, depending on whether it's falling or what's occurring to it. And objects can also move in and out of the system. So I can actually take that candy bar out of the system and put it in my mouth if I want. And we can keep track of those kinds of things when we're talking about open systems. So the big concept of conservation of mass can actually be dealt with either with open or with closed systems. Let's start with talking about closed systems. So conservation of mass in a closed system means that in any instant in time, the total mass of the objects in a closed system should be constant. So I can make a system out of any objects, and I can figure out where their mass was at any instant in time back to the beginning of history, or I can figure out where that mass is going to go billions of years in the future. So the mass in the universe is the same. We are never going to get any more stuff in our universe than we have right now. It's constant. We have the same amount of mass right now as we've had at every instant since the Big Bang. So if I wanted to make an approximately closed system containing of Miss Nichols and a Hai-Chu, I could put us both inside the same system. So there I am. I'm about 65 kilograms, and the Hai-Chu is about 0.0025 kilograms before anything happens to it. We're both in the system. The total mass of the system is 65.0025 kilograms. Okay. If I decide to eat that Hai-Chu, peel off the wrapper, and put the Hai-Chu in my mouth, then the total mass of the system is still the same, 65.0025. It's been distributed slightly differently, right? I'm chewing that, it's delicious, but the wrapper has a little bit of mass, and now so the wrapper has lost a little bit of mass, and I've gained a little bit, but the total mass in the system is still the same. Of course, you talk to us 10 minutes later, we should still have the same total mass. That Hai-Chu is now in my stomach, and actually those are hives on my face because I'm allergic to mango, which was unfortunately in the Hai-Chu, but at any rate, the total mass of the system is going to be the same. So you could follow the system forever, and we'd be able to keep the same total amount of mass as it started with. We can express the same idea of conservation of mass using open systems. It looks a little bit more complicated with open systems because we have things moving in and out, which means that the mass in an open system is actually changing, but you can track it and you can figure out where it came from and where it went to. And even though it looks like the mass of this open system is changing, no mass is actually disappearing. It's just moving in and out of the system. So the mass is all still there, it all still exists, it just has moved into a different system. So let's look at a slightly different example. Example of buying frozen yogurt and eating it and then figuring out what's happening to that system. So let's start with this frozen yogurt in the cup has a mass of 250 grams. That's my original system, my before system, and that means the total mass of that system is 250 grams. That's the only thing that's in it. Maybe I'm going to add some toppings. So I'm going to put some gummy bears in there, 20 grams of gummy bears and 30 grams of hot fudge. I think if you take a quick look at that, you can figure out what the mass of the system becomes right before I eat it, right? 250 plus 20 plus 30. So now my system's mass has changed. The total mass is 300 grams. That doesn't mean we created mass. It just came from outside to inside the system. Now if I eat all that stuff, I'm going to take some mass out of the system. So I've got an out arrow leaving my system, and I'm going to take out 230 grams of delicious assorted food and take that out of that system. Now that means the total mass of the system is 70 grams, which is probably just the cup and whatever drips that I couldn't get out. So the mass of the system's changed, but it's just because objects have moved in and out. Okay, so a quick summary of this video. First, you're going to find as we move through physics, it's really useful to define systems for any object you're interested in analyzing. You should think specifically about whether it makes sense to use an open or a closed system, and also which objects should you include inside the system and which objects are outside the system. And then the big idea that the total mass in closed systems is conserved. So the universe, which is kind of the most important closed system, the total mass in our universe will always be the same. Thanks for listening.